Swayam Prabha. Digital India. Educated India.
Good morning, and we'll continue from where we left off last time. We were solving this problem of stratified flow, two immiscible fluids flowing side by side, okay, and we want to get the velocity profile in this system, okay. What we had done was we used the equation of continuity and found that the component of velocity perpendicular to the flow was 0. And now we want to see what information we can get from the momentum equation, the Navier-Stokes equation. The important equation is, let me draw that system again. This is small h and this is capital H. This is fluid 1 and this is fluid 2, okay. This is the x direction and this is the y direction. So, since the flow is in the x direction, the momentum balance which is really going to be of interest to us is the x momentum balance, okay. And we wrote that last time. And this turns out to be T plus U1 du1 by T. So, this is basically the Navier-Stokes equation which I am writing in the x direction. Equals, now because that guy has come there, I am going to write this as minus dp1 by dx plus mu d square by dx squared plus u1 dy squared plus d square u1 by dz squared, okay. This is the viscosity, this is the pressure in the first fluid. So, the subscript 1 tells you it is the first liquid, okay, and u is the velocity in the x direction. So, u1 is the velocity in the x direction of the first liquid, okay. So, u1 is velocity in the x direction of the liquid 1. So, what we want to do is we want to see if we can simplify this equation. Now, how can we go about simplifying this equation? By using some of the information we already have got, some of the assumptions which we have already made. So, we are saying this is let us say a steady state flow. If you assume steady state, because you are just running your pumps for a long time, okay. So, you can wait, you have waited sufficiently so that your system has attained steady state. Things are not changing with respect to time. At any point, okay, in the system, things are not changing with respect to time. That is what it means. That means the partial derivatives are 0, okay. This means at a fixed point, there is no change in the variables with respect to time, okay. So, this implies what? du1 by dt is 0. Okay. When is this going to be valid? If you have been running your micro channel for a long time. So, you have waited for all the initial transients to decay and then you have steady state, and normally we will be running it for a sufficiently long time, right, any reactor, any system. The other thing we know is, we have already shown V1 is 0 from the continuity. From continuity, V1 is 0. So, this goes to 0. So, V1 du1 by dy is 0, because this term has V1. We have assumed fully developed flow. Therefore, du1 by dx is 0, right. Fully developed means there is no change. Whatever you see at a particular x is the same as some other x. Okay. So, du1 by dx is 0, and this implies that u1 du1 by dx is 0. And because we are assumed infinite plate in the z direction, there is no velocity in the z direction. So, w1 is 0 because in the z direction system extends to infinity. Okay. So, there is no variation in the z direction. So, what does this mean? Because W1 is 0, this goes to 0, because V1 is 0, this goes to 0, fully developed flow that goes to 0, steady state that goes to 0. So, the left hand side basically is vanishing. Okay. So, I have 0 equals minus dp1 by dx. Now, I told you that there is no fully developed means there is no change in x direction. Does that mean d by dx of P1 is 0? No, because the pressure gradient is the one which is driving the flow. Okay. So, d by dx is 0 for the velocities, velocities are not changing, but there has to be a pressure gradient. Unless there is a pressure gradient, you cannot have a flow. Okay. So, dp1 by dx is not 0. Okay. Remember that. And when I come to this Laplacian here, because of fully developed flow, this becomes 0, right. du1 by dx is 0 everywhere. So, second derivative will also be 0, and we are saying there is no variation in the z direction because it is extending to infinity. So, because of that, this goes to 0, this goes to 0, okay. And what I am left with is plus mu d square u1 by dy squared. That is my simplified equation. Okay. Now, I want to explain that d square u1 by dx squared is 0 because of fully developed flow, and d square u1 by dz squared is 0 because system extends to infinity in the z direction. So, in the z direction there is no change in the z direction because it is infinitely long. I am looking somewhere in the center, that is the thing. Okay. So, this is basically what you get by simplifying the Navier-Stokes equation in the x direction. So, what this means is the pressure gradient is driving the flow, and that is balanced by the viscous forces. I could do a similar thing for the second fluid, right, and for the second fluid also I will get a similar equation. Okay. So, basically what I am saying is I write the equation here, mu 1 d square u1 by dy squared equals dp1 by dx. This is in the first liquid. When you write a differential equation, you need to also specify the domain over which it is valid. Okay. I mean, you remember the math course we did, we said this is valid from 0 to A. So, this is the first fluid. So, what is the domain over which this is valid? From y going from 0 to h. Okay. This is valid for 0 less than y less than small h, because this is in the first liquid. If you wrote the equation for the second fluid and did a momentum balance, you would get a similar equation which says mu 2 d square u2 by dy squared equals dp2 by dx, correct? Okay. And this is going to be valid in what domain? Small h less than y less than capital H, because the second fluid extends from y going from small h to capital H, and the first fluid from 0 to h. So, this is the momentum, simplified momentum equation. I just didn't go through the same arguments again, okay, but you will get the same thing. Only thing is, instead of subscript 1, you have subscript 2. So, yeah. So, what we have is a second order equation, okay, and typically one way to look at it is the flow is generated by the pressure difference. So, there is a pressure gradient and that is imposed by the pump is giving a pressure gradient and that is generating the flow. What I am trying to tell you is that the pressure gradient is normally known to you, maybe, okay, and if the pressure gradient is known to you because you know what the pump is, that is dp1 by dx on the right hand side is known quantity. It is like a non-homogeneity, okay, that you have. So, dp1 by dx is known, and this is basically a second order equation. So, because the second order equation, I need to have boundary conditions to solve this, okay, and u1 remember is the velocity in x direction. So, we need boundary conditions to solve this, okay. What are the boundary conditions we are going to put at y equal to 0? We have the no slip boundary condition, that is there is no relative velocity, the wall is stationary, the liquid is also going to be stationary. So, the no slip boundary condition implies u1 is 0, okay, at y equals h. And y equals h, h is the interface between the two liquids. I assume, I mean, we are going to have a physically realistic field, which means the velocity is going to be continuous. The velocity of the first fluid at h is going to be equal to the velocity of the second fluid at h, okay. You can't have one liquid going at a velocity, another liquid slipping past it at a faster velocity, that is physically unrealistic. Okay. So, we say velocity is going to be continuous. I say u1 at y equals h equals u2 at y equals h, okay. And then I have at y equals capital H, which is the other wall. What is the boundary condition I am going to put? Again, no slip boundary condition. I am going to put u1 equals 0. Is this right? At the upper wall, you do not have the first fluid, you only have the second fluid. It can't be u1, it has to be u2. Okay. So, at the upper wall, it is u2 equal to 0, because the first fluid does not exist at capital H, okay. So, I have only 3 conditions and I have 2 second order equations. This guy needs 2 boundary conditions, this guy needs 2 boundary conditions, I need one more boundary condition, right. The other boundary condition is going to come from the fact that the forces, the stresses exerted by one liquid on the other are going to be equal and opposite to the not equal, equal to the force exerted by the second fluid on the first. So, there is a continuity of the stresses that are going to be exerted. Okay. So, the fourth boundary condition, because I need 4, is going to be given by that condition of continuity of shear stresses. The fourth boundary condition is continuity of shear stresses. That means, what I want to say is that tau 1 yx is equal to tau 2 yx. Okay. Again, subscript 1 is for the first fluid, and this is only at, I mean, this is, we are talking about the boundary condition, this is at y is equal to small h. Okay. 1 is the first fluid, 2 is the second fluid, and yx, and we are going to discuss this in more detail later on in the course, okay, what exactly I mean by tau yx. The first subscript tells you the direction of the perpendicular to the interface. So, interface is in the x direction, the perpendicular direction is the y, okay. So, this is the direction of the, so this is the direction of the normal to the interface, and the second subscript is the direction of the stress. So, when you talk about shear stress, you normally specify 2 things. One is the direction of the normal, it is acting on a surface, okay. The direction of the normal to the surface is the first subscript, the direction along which the stress is acting is the second subscript, okay. Anyway, we will see this in some more detail. So, this is what it is. So, now if you assume your fluid is Newtonian, then you can use the Newton's law of viscosity and relate these shear stresses to the velocity gradients, okay. So, this becomes for a Newtonian fluid, mu1 du1 by dy plus dv1 by dx, okay, and we will derive how this comes later, equals mu2 du2 by dx du2 by dy plus dv2 by dx. Okay. This is the relationship between the velocity gradient and the shear stress. Okay. So, I mean, one way to remember is x and y. So, x component of velocity and y component of velocity come, and because the shear stress, it is differentiated with the other thing. U1 is in x direction velocity, derivative with respect to y. This is the y component of velocity, derivative with respect to x. Okay. So, same thing here. Now, what we already know is that V2 is not changing, everywhere V2 is 0, V2 does not change with respect to x at all. So, this goes to 0 because of the continuity equation where we showed that velocity is 0 everywhere. So, velocity is 0 everywhere for all x. So, dv1 by dx is 0, dv2 by dx is 0, okay, and this simplifies to mu1 du1 by dy equals mu2 du2 by dy. So, that is your other boundary condition, this is your fourth boundary condition, okay. So, basically you need 4 boundary conditions, and I have told you what the 4 boundary conditions are. Before we solve this, I want to look at the y momentum equation and see what kind of information we are going to get from the y momentum equation, right. Because there are 3 momentum equations x, y and z. So, x is the one which is important because it's driving the flow, but when we still have y and z, let's see what happens, what information we get. If you look at the y momentum balance, again I am going to do for only one liquid, rho 1. Now we look at the y momentum, so the velocity component is v, okay. By dz equals minus dp1 by dy plus mu 1 d square u v1 by dx squared that is your y momentum equation. Now we already established that v1 is 0, okay. So if v1 is 0, that means what? This will be 0 because of v1 is 0, I mean this goes to 0, v1 is 0, so dv1 by dx is 0, v1 is 0, that goes to 0, this goes to 0 because this v1 is 0, no change in the z direction, okay. Basically what this means is everything goes to 0 and we get minus dp1 by dy equals 0. Pressure, what does this mean? Pressure is not a function of y. Pressure does not vary in the direction which is perpendicular to the flow. Pressure is uniform everywhere, okay. This implies pressure P1 is not a function of y, it is a function only of x, okay. So pressure P1 is a function of x alone because in the z direction there is no variation also. In the z direction again, I mean there is no change in the z direction, so the pressure does not vary with respect to y, pressure does not vary with respect to z, okay, and pressure is a function only of x, okay. So dp1, so pressure is independent of y, so p1 is a function only of x. You can do the same thing for the second liquid, okay. The second liquid you will get P2 is a function of x, okay. So basically what I am saying is pressures are just a function of x. What this means is when I look at okay, the right hand side, this is a function of x, it is not a function of y, we already showed that from the y momentum balance. And what about this? This is a function of y. Why is that? Because of fully developed flow u1 is not a function of x, okay. u1 is not a function of x because it is fully developed, so it is a function only of y. This guy is a function only of x, so there is a function of y here, there is a function of x here. So from this what do you conclude? A function of x can be equal to a function of y only if both of them are a constant. So this guy must be, so this must be a constant, okay. So basically dp1 by dx is constant, which means pressure is varying linearly with respect to x, okay. So P1 and P2, because P2 will be similar, okay, vary linearly with respect to x. Okay. So, what you need to do is understand that mathematics is giving you some information. How does that translate to a physical insight? Okay. So, now because this is a constant, I can treat dp1 by dx as constant. You can integrate this equation 2 times and find out velocity, correct? I mean, if it is a function of y, you have a problem, but I showed you it is not a function of y. So, basically you can integrate this equation once, integrating, what do you get? Mu1 du1 by dy equals dp1 by dx multiplied by y plus c1, right? Because it is a constant, I can just, you know how to integrate this. And the second thing is mu1 u1, integrate one more time, you get dp1 by dx times y squared by 2 plus c1y plus c2. You know, I should have been smarter. I should have put this mu1, because this is also constant, this is also constant. I could have kept these two constants together, but anyway, I didn't do that. So, I kept it like this. Now, you therefore, this is how the velocity varies with y for the first fluid. You can do a similar thing for the second fluid and you will get a similar expression. For liquid 2, I will get mu2 u2 equals, use my viscosity, u2 equals dp2 by dx y square by 2 plus c3y plus c4. C3 and C4 are these arbitrary constants which come from the integration, okay, which we have to find out, and we find that out by using those boundary conditions that I listed. So, I had 4 boundary conditions, I have 4 constants, I find those constants by using those boundary conditions, okay. So, that is something I want you to do. I want you to, I have given you the expressions for u1 and u2. So, use the boundary conditions and find the constants C1, C2, C3, C4, okay. Using the boundary conditions, find C1, C2, C3, C4, and then what do you have? You will have an expression, you will have an expression u1 will be a function of, what will be the right hand side containing? Function of dp1 by dx and small h. u2 will be a function of dp2 by dx and small h, okay. So, what I am saying is the width of the channel capital H is fixed. What I do not know is the interface position, because I am pumping 2 liquids, okay. So, there are 2 ways to solve this problem. If you want to solve it mathematically, okay, I have h, I can assume a small h, because then the velocity is known to me, okay, and I can find what is the flow rate of the first liquid. How do I find out what is the volumetric flow rate of the first liquid? It is just integral of u1 dy from 0 to h, right. So, I mean, we are talking about flow rate per unit length, okay, because I am not looking at the dimension in the z direction, okay. I am going to prove later that dp1 by dx is equal to dp2 by dx, okay. So, right now what you have is that 2 equations in 4 variables, okay, u1, u2, small h and dp1 by dx, they are the variables you have. So, if I tell you what the pressure drop is, if I tell you what the interface position is, small h is, you can calculate u1 and u2, Okay. So, basically what I am saying is 2 equations, 4 variables, okay, which is dp1 by dx small h u1 u2 given. So, I can fix 2, find the other 2, okay. So, we can fix dp1 by dx and the interface position, find u1 u2, okay. Then how do I find q1, the flow rate? It is 0 to h u1 dy and q2 is integral small h to capital H u2 dy, right. That is how you define the flow rate, because the velocity is not constant. If velocity is constant, it is u1 into small h, u2 into capital H minus small h, because velocity is varying as a function of y, you have to integrate it. Now, so if you are given the pressure drop and the interface position, you can calculate the velocity by putting the boundary conditions and all that. You can calculate the velocity, okay. You can integrate the velocity which you found out from 0 to h and small h to capital H, find out q1 and q2, everything will be in terms of an expression, okay. So, you can get q1 divided by q1 plus q2 as a function of dp by dx and small h, okay. So, we are assuming that dp by dx is known and h is known, small h interface position is known. Find the velocity, find the flow rate, then you find the, so this tells you the flow rate fraction q1 divided by q1 plus q2, and remember we wanted to find out the relationship between q1 by q1 plus q2 and h. So, basically this is what you have gotten. Our first objective was, what is the relationship between the flow rate fraction, okay, which is this, and the hold up is small h by capital H, okay. So, the other thing you can do is, mathematically this is easy to do, but experimentally you are possibly going to be pumping in 2 fluids with specific flow rates. I mean, you are not going to keep doing an experiment to fix the h. H will be a dependent variable. The hold up, the interface position is going to be a dependent variable. When you do an experiment, you will just turn on this pump, turn on that pump, the pumps will pump the 2 liquids inside, right. H is going to be found out, H is not known. So, in an experiment, so from the mathematical point of view, this is the way to do. From an experimental point of view, you have to do the ulta. Q1 and Q2 are given, and you will find what the interface position is. See, I told you the 2 equations and 2 unknowns, 4 unknowns. So, you will fix Q1 and Q2 by integrating these equations, find out Q1 and Q2, find small h and pressure gradient, okay. So, we have 2 equations, 4 unknowns, you fix 2, find the other 2. Experimentally, I will fix the flow rate and find what is the pressure gradient and what is the interface position, okay. Or you can do the ulta, anyway I have 2 equations, 2 unknowns, put 2 values, find the other 2. Is this clear? So, mathematically speaking, the way it is, it looks like h is an independent variable, but h is actually a dependent variable. H is not known in an experiment, right. You will experimentally measure the interface position and then you will make a note, for this flow rate fraction I am getting this hold up, for another flow rate ratio I am getting this hold up, okay. So, now that is basically what it is, and what I want you to do is do this exercise and plot the flow rate fraction versus the hold up, okay. I want you to do this homework, okay. So, find Q1, Q2 as a function of dp1 by dx and small h, okay, and plot q1 by q1 plus q2 versus h by small h. You see, these are all dimensional fractions, so they are dimensionless, right? Small h by capital H is a fraction, q1 by q1 plus q2 is a fraction. So, we are talking about dimensionless numbers now, okay. So, I want you to do this and make this plot, okay. Yeah, that is the first thing. Now, I told you dp1 by dx equals dp2 by dx. Okay, and how do you come to that conclusion? You come to that conclusion by doing what is called the normal stress balance along the interface. Okay, we balance this arises from the normal stress balance across the interface. Normal stress means which is perpendicular to the interface. So, I am going to do a stress balance in the y direction. So, because my interface is in the x direction. So, this is my x, right, interface, and this is y. So, what we are earlier we spoke about continuity of shear stresses. Now, I am talking about continuity of normal stresses. The normal stresses also have to balance each other because interface is that, and the way the normal stress is defined in this particular problem is pressure is acting in the normal direction, right, minus P1 plus 2 mu 1 dV1 by dy equals minus P2 plus 2 mu 2 dV2 by dy. The normal stress, we are looking at the y direction and velocity component also in the y direction. We will again derive this. My point is V1 is 0 everywhere. So, dV1 by dy is 0, V2 is 0 everywhere, again no vertical component of velocity. So, dV2 by dy is 0, and so this goes to 0, that goes to 0, and what remains is P1 equals P2. Okay. So, you will get dP1 by dx in the first fluid, dP2 by dx in the second fluid, but because this interface is flat, the pressures are equal. Okay. So, dP1 by dx is equal to dP2 by dx. So, it is not that you can independently control. If you want to have a flat interface, okay, we are assuming that you have a stratified flow, that means there is no pressure variation in the y direction at all, even across the interface. Okay. So, this means that this is of course at y equal to small h, because I am doing the normal stress balance at the interface. Okay. At the interface I am saying the normal stresses are balanced, and this is how the normal stress is defined. Okay. So, now anyway, so this is something which you are going to see in the course. I mean, how the shear stress is defined, how the normal stress is defined, and that is what it is. I keep putting this duster somewhere. Okay. So, what is it that has allowed us to come up with this analytical solution? The fact that the terms on the left hand side are 0, okay, because the terms on the left hand side were the ones which are contributing to the non-linearity of the system. The equations were non-linear because of the inertial terms u1 du1 by dx, v1 du1 by dy, those terms were the ones which were making non-linear, okay. But with the kind of assumptions we have made, okay, we were able to knock those off, okay, and we have a bunch of linear equations. This is what we talked about earlier, linear second order linear system which is non-homogeneous, okay, because the pressure gradient is your non-homogeneity, okay. So, the key points which I just want to summarize are pressure P1 equals P2 across the interface, and therefore dP1 by dx equals dP2 by dy, dP2 by dx, okay. And the system behavior is determined by mu1 and mu2, the viscosities. The density does not show up, it is independent of the densities of the two fluids, because there is no density, right. The density was multiplying the inertial terms on the left hand side, that disappeared, okay. It is independent of the density of the two liquids. Okay. Yeah. Now, so again, what I want you to do is get this flow rate fraction done, and if you have some difficulty, you can talk to the TAs, they will help you. I want to basically go to, because it may be difficult for you to think of this infinite plate and all that. So, what would be a more sensible problem to solve would be possibly the same problem in a cylindrical geometry. Let us talk a bit about the extension of this to a cylindrical geometry. So, now the cross section is going to be circular, okay, and again I have two fluids flowing side by side. So, this is my circular geometry, and this is the center, let me draw this as a solid line, center, this is the axis, r equal to 0, the radius of the cylinder is capital R equal to capital R. Two fluids are flowing. Now, when you talk about two fluids flowing side by side, it is going to be like this is one fluid, okay. This is the core fluid and it is surrounded by an annular sheath. So, there are two fluids flowing inside my cylinder. One fluid is flowing in the core central region, okay, and it is surrounded everywhere by another liquid. Could be one could be oil, one could be water, it does not matter, okay. So, now this is again two fluids flowing side by side, same as what we discussed earlier. So, that is the thing you have to understand. That was stratified flow, this is also stratified flow. Only thing is, here one fluid is completely surrounding the other fluid, okay. And what do we have? Yeah. So, what is the, again we have liquid flowing in this direction, and in the cylindrical coordinates, what are the three coordinates we look at? R, theta and z, okay. In cylinder, we have R, theta, z. Now, the flow is in which direction? Flow is in the z direction, okay. This is my z direction, this is my r direction. Clearly, the velocity component which is dominant is going to be the Vz. Vz is the one which is there, okay. So, this is equivalent to my u earlier. Vz is my velocity component and is a function of r, okay. We had u1 is a function of y, earlier. So, now we have Vz as a function of r, because it will vary in the radial direction. In the radial direction, velocity is 0 at the boundary, right, at the solid wall, and it is some solid value in the middle. So, this is similar to u1 is a function of y. In the rectangular problem, I assumed z was infinity, right, that is the third coordinate. So, what is the third coordinate here? The third coordinate here is theta, okay. So, what we are saying here is, here the third coordinate is theta, and we are going to say d by d theta is 0. What I am saying is, if you look at the cross section, okay, this is theta equal to 0, this is some theta, forget, this is theta equal to pi, this is theta equals pi by 2, and this is theta equals 3 pi by 2, okay, this one. So, if you look at it from the cross section, we have the velocity varying only in the radial direction. The velocity variation in the radial direction here is the same as the velocity varying in the radial direction here, same here. That is, there is no change with respect to theta, okay. So, we say that this is the axisymmetric assumption, because in the geometry the outer wall is not changing with respect to theta, capital R is fixed, the core interface, this is the interface, right, this is R1, let us say, interface is at R1, okay, this is the core is in the middle, annular is outside, okay, when you look at the cross section. So, this is also not changing with respect to theta, that is not changing with respect to theta, and I am saying velocities do not change. So, this axisymmetric assumption tells me d by d theta is 0. In that case, the infinite wall assumption told you that d by dz was 0, okay, that is the analogy of this. So, assumption, this is analogous to the d by dz equal to 0 for the infinite wall problem in rectangular Cartesian coordinates, okay. So, I mean, so again this problem is also a one dimensional flow problem, where you have only one dominant velocity component varying in a direction is perpendicular to the other one. So, if you were to simplify the equation of continuity like we did, the equation of momentum, you will get similar kind of simplified equations which you should be able to integrate and find what the velocity profile is, find what the flow rates are as a function of capital R1 and small r, capital R, okay. So, I think the message I am giving is, when you go from one coordinate system to another, the kind of physical behavior is similar, mathematics may be slightly different, okay, and you have to understand this analogy to help you interpret the results and get insights in a better way, okay. Thank you.